giving me a chance to talk our recent research here. Here is very exciting, interesting meeting. I'm Shinichi Mori from Japan Mathematical Agency in Spring Lake. This is a picture of Spring Lake. And we have been doing the outlet study for urine compounds for these more than 10 years. And I'd like to take this opportunity to show you some of I had some opportunity to write a review paper about our study. So I'd like to take this opportunity to introduce these papers. The one paper has just recently appeared in Journal of Physical Study of Japan, which summarized our archive study for urine compounds, representing the bond structure and film surface of from ideal compounds to helium compounds, or heavy chromiums, or heavy compounds with ferrite powder in the spherometry states. So this is a kind of database of the electric structure and uranium materials. And in this paper, we also try to understand the collateral spectrum of the uranium compounds. The collateral basically represents the local electric structure of the atom. And here we try to understand how the collateral can be understood. Here representing 90 collateral spectrum of 90 uranium compounds. And you know, the collateral is very sensitive to, for example, the balance state of uranium. It is very important expert parameter for uranium compound, but it's not still well understood. So here we try to understand that these, for example, the balance number from these comparison of these spectrum. In other paper appeared in Journal of Physics Fundamental Matter recently, and in this paper we tried to understand the compound, fourth compound also, and here I focused on few materials like Cerium-115 or Ytterbium-232 or Uranium-232. Especially this compound, there are so many others papers nowadays, and there are many discrepancies between these studies. So here I try to make a unified picture of this IS study. So I'll be very happy if you are interested in these papers. Okay, let me come back to my research today. It's not outwards, but it's resonant emission. Here, title of my talk is Imaging of Further Electric Structure of Uranium Compounds by uranium-40 pilot resonant emission. This study has been done with a collaboration with many people. The emission experiments have been done with the collaboration of staff members of JAE and Spring Lake, those people. And we also have collaboration with Professor Fujimori of the University of Tokyo. And band structure calculations has been provided by Professor Yanagami of Kyoto University. And high quality single crystals have been provided by Professor Dr. Hama and Yamamoto at JAE and Tokai and Professor Onuki of the University of Philippines. We also have funding support from some funding supports. One of them is what we call J-Physics. That is a 5-year project. Here J stands for not Japan, but total angular momentum J. And here we will study the physics of conductive multiple systems. Hopefully we will be able to find new physics and new materials during these studies. And this is the outline of my talk. As an introduction, I want to briefly explain about resonant emission. Then I want to apply the method to some uranium compounds. First, I want to show the result of the ideal compound uranium-3, which is most simplest case. Then I want to proceed to a more interesting material, heavy material, which is UPD03. And finally, I want to show the result of some globalized case. And finally, I would like to conclude the results. And I think most of people here are familiar with resonant emission, so I just want to briefly remind you what is resonant emission. here, here I'm showing you some core level and unoccupied open shell. Here I'm assuming this is 4F and this is 3D. This should be 10 electrons, but I'm showing just 2 electrons. In normal photon emission process, this 4F electron are excited by the incident photon. This is simple normal type photon emission process. But if you tune the photon energy to this 3D 4F absorption energy, you have different process. And if you tune the photon energy to this absorption energy, then you can excite this 3D electron to 4F level. And this state can be OJ decay can occur like this. And this process is called the supercapacitor cloning. And these two finite states are exactly the same. So by tuning the photon energy around this absorption edge, you can interfere these two finite states. And this is an example of the resonant photon emission experiment for Selin engine 3, and this is XAS, Selin 3D 5x2H. And there are many multiple structures, but these are absorption edges. And these are balanced band spectra measured at various photon energy. And as you can see, the excitation energy approaches to the edge, and the contribution from Selin 4F is enhanced. So by using resonant photon emission experiment, you can understand what is the contribution of specific photon. So this resonant photon emission has been applied for FLFMA materials. And here, for example, for Selin materials, Selin 40H, which is about 122 electron volt, has been well used. This is a very classical example. This is a resonant photon emission spectra of Selin UD2 reported by Jim Allen about 30 years ago. And as you can see, the energy approaches to the absorption edge. There's a strong enhancement of Selin 40 edge. And for Selin compound, there's another edge, which is 3D edge. The energy is much higher than this energies. And if you use the higher photon energies, you can have much enhanced photon sensitivity, as demonstrated by Sekiyama with Suga in Nature in 2001. Here, these are comparison of the Selin 3D and 4D resonant emission. Basically, this spectra and this spectra are measuring the same compound. But as you can see, if you change the absorption edge, the spectra are totally different. This right panel also shows the same but totally different. So this is probably due to the different size sensitivity of this external technique. This is ENS technique with acid electron in solids, and it has minimum around 50 or 100 eV. So if you use the Selin 40H, the kinetic energy for the electron is somewhere here. So it is about 6 constant something. So it is almost a lattice constant of the material. So basically, you can have information on these surface. But if you go to 3D edge, the mean class is somewhere here. It's nearly 20 ohms. So you have 2 or 3 layers. So you have much enhanced drop sensitivity by using higher absorption edge. And for uranium compound, 5D absorption edge have been used. Energy is about 108 electron volt. Here are some example of the uranium 5D 4F resonant emission. This solid lines represents the home resonance spectra, and this dashed line represents the off resonance spectra. And this circles represent the difference of these spectra, so representing the partial fiber spectra. So this technique is very useful, but as we learn from the case of cerium, these energies, you have large contribution from the surface. So it is important to use a much higher contribution. So for uranium, there's a uranium 40H, which is about 736 electron volt. So you can have much enhanced processivity. However, it has been reported there's no resonant enhancement, 740H. These are data of uranium reported by Jim Allen about 20 years ago. And this is XAS spectra, and this is these are balanced band spectra measured at on resonance and off resonance condition. As you can see, there's no enhancement. The spectra are essentially the same. They normalize the spectra with the shape of the spectra, but even they are essentially the same, so there's no enhancement. So when we started the experiment for uranium, we briefly checked this result. This is the spectra of the uranium platinum barium 5, and excited by different photoenergies. The absorption is somewhere here, and these are platinum 5F, and these are uranium 5F. And as you can see, they are essentially the same, no change. So, okay, there's no enhancement. So after that, we didn't do that resonant emission experiment. But 5 years ago, Jim Tobin and co-workers reported the uranium 40 5F resonant inverse photoemission. Inverse photoemission is basically the inverse process of photoemission. So it is electron beam photon experiment. And this is an XES, X-ray emission spectra of uranium 40 5x2H. And these are resonant inverse photoemission spectra. As you tune the energy of electron to 40H, there's some enhancement here. There's some satellite, and this satellite also some enhancement. So we were very surprised to learn this result. So we decided to study the resonant emission very precisely. So this is the result. This is an XAS spectra of uranium aluminum 3, and these are balanced band spectra. But my horizontal axis is kinetic energy and plus work function. That means the Fermi energy is located at this excitation energy. And as you can see, there's some finite enhancement here. If I assume here is 1, then this is 1.15. So clearly we have some enhancement, but it is very weak. So it is so weak that we didn't realize it. So why the enhancement is so weak? This is my guess. This is my guess. And the resonance is described by the famous Fano formalism. Enhancement factor is expressed like this, and the Q is the Q that characterizes the enhancement. When the Q is large, then you have large enhancement. But the Q is small, you don't have the enhancement. The Q is the most simplest case. The Q is represented like this. It's a ratio of the matrix element for DF absorption and matrix element for the electron potential. So now I'm going to focus this. This is a total cross section of cerium and uranium. Green curve represents the cross section of cerium, and red curve represents the total cross section of union. So if you look at the same foliage, there's a huge jump, meaning the matrix element is large. And in 48, there's also the absorption, this matrix element is very large. But if you look at the 3D, there's still large jump here. So this element value is large. But if you look at 48, this jump is very small, meaning that this value is suppressed 48. So this might be one possible explanation why the enhancement is very weak at 48 edge. So anyway, the enhancement is very weak, but still we can use it. So from now, I want to show you the result of the result condition. So again, I want to show you the result of uranium aluminum-3. Aluminum-3 has an 18 case. Uranium aluminum-3 has a cubic type crystal structure, and which is a paramagnetic bound. And it is considered uranium-5 is considered as kind of a very uncoherent electric structure, and the gamma value is not so large. So, and this set of panel represents a summary of resonant potential for the cerium aluminum-3. This is X-ray spectra, and this is the spectra, valence band spectra measured at 725 electron volt here. And this image represents the valence band spectra as a function of excitation energy and binding energy, but it is subtracted by this spectrum. So this image representing how much the spectra is increased or decreased relative to this spectrum. So clearly you can see enhancement here at the absorption edge. So in this panel, I made a different spectra, subtracting off resonance spectra from on resonance spectra. And this is the result. And here I'm roll up of this different spectra. The spectra shows a very sharp peak under the energy and having long tail toward the higher value energies. And this is the typical spectral line shape of anti-ionic bound. So although the band structure calculation is under progress, but I believe this can be well described by the band structure calculation. So let's move to a more interesting compound, which is UPDZ3, which is heavy volume superconductors. There's a hexagonal type crystal structure, and shows a anti-ferromantic transition at 40 Kelvin, and it also shows a superconducting condition at 2 Kelvin. And gamma value is very large, so this is heavy volume. And this is the same set of panels as we showed in the previous slide. And as you can see, there are some enhancements for the edge here. But there's but interesting point is that in addition to the ferrum edge, there are some features, streaks appear here. And this is the procedure of making the different spectra, subtracting of resonance spectra to on-resonance spectra. And this is a comparison of different spectra and band structure calculation of pressure filing density states. And here we have something here which cannot be explained by the band structure calculation. So probably this is due to the incoherent part of the spectra, which is beyond the LDA. So in the case, the most of the spectral rate explained by the band structure calculation. But if you go to heavy volumes, there's some deviation which cannot be understood by the band structure calculation. So then I want to show you the result of the localized compound. here representing the case of uranium gallium 2. This compound is believed to be a localized compound because it is a ferromagnet, but the moment is extremely large, and the gamma values are very small. So it is believed that 5 electrons are almost completely localized and doesn't have contribution to the Fermi energy. And this is a result of the emission. And as you can see, there's some enhancement on the Fermi energy here, but most of the 5 component is here, about 0.5 to 1 electron. And this is a procedure of making different spectra, and this is the roll-up of different spectra. So as we can see here, most of the here, higher primary energy side. There's something near the Fermi energy, but its contribution is very small. So this is very local. So now we want to understand how the localized state looks like in neutron space. So this is the resonant RPS spectra of uranium gallium 2. So this is the RPS spectra measured on this orbital resonant energy. And now we are measuring this cut in momentum space. And this is RPS spectra. As you can see, there are many clear dispersions, and the important thing is that this localized component has very large energy dispersion. So it is not straight line, but hybridized with other Riemann state and showing some large energy dispersion. So this is I think this is a very important point, that localized component has some finite momentum dependence. So the final example is UBD3, which is also known as the localized finite compound. And this is these are a set of same pattern, and as you can see, there's some enhancement here, but there are some strong signals here. So so this is a constant initial state spectra, meaning that fixing the binding energy and changing the instant photon energy. And if you look at these states, it shows some enhancement of absorption edge. But this feature here has nothing to do with this absorption edge. So probably this is due to the paradigm 40 state. It has some strong photon energy dependence. So there should be some further contribution here, but paradigm 40 has large dependence on photon energy. So here we can see the contribution from 5. This is the procedure. Anyway, we made a different spectra here. And this green curve represents the different spectra. As you can see here, we didn't have meaningful result. And this red curve represents the different spectra, but using very different photon energies. By using very different photon energies, you have somewhat different cross-section for radium 40 and radium 5F. So by subtracting these two different photon energies, then you can have some 5F partial densities. So here we have some good agreement, but here no. Paradigm 40 contribution is killing this testing. So we cannot use this as a different step. Okay, these are this panel shows the alpha spectrum at in-resonant condition, and as you can see here, very strong flat dispersion here. And this is one source of calculation for thorium radium 3. And thorium, of course, there's no effect on the thorium case. So if you compare with this and this, here very strong intensity here. So this should be 5F. somehow division on uranium-4E and uranium-5F. And it also shows some dispersion. It's very small, but it shows dispersion. So again, the localized state finite dispersion, and meaning that some finite hybridization. Okay, let me conclude. This is the summary of my result. So from beginner compound to localized compound, we have found some systematic changes. The peak in the ferrometallurgy intensity decreases, and the other localized component increases. So it's very short successfully. Thank you very much.
So, a quick question. If I draw sort of the simplest kind of diagram people tend to use for resonant scattering processes, where I have a core level, I have some itinerant valence levels, and I'll take a core electron, put it in an unoccupied state, and then I'll allow one of the low energy electrons to decay to fill the core hole, and at the same time I'll get an electron out. In that sort of picture, one is left wondering, if I started by putting an electron in an unoccupied level, and I don't necessarily have to decay back down with the same electron, what are the odds that you're leaving some multiple excitation, both something with both this, like a normal ARPA spectrum, but plus some other excitation thrown in? I've noticed that doesn't seem to happen very much in resonant photo emission, but is there an explanation as to why that is?
I'm sorry, I don't have an answer to that question, but actually we measure the photo emission spectra at the absorption rate in very wide energy range to see that is there any decay channel, but substantially no other decay channel. I don't know why.
Yeah, well, I know that the electron you promote in the first place kind of has a good symmetry for going back down again. So there may be good headway. Anyway.
In the series of compounds, where you look at the photo emission, there's not very much dispersion, except the amplitude drops. That's what it was. In uranium systems, we didn't show much of peaks or something like that in the spectrum. I was wondering if there's any evidence amplitudes jumps as a function of Cuban energy changes.
Unfortunately, is there any? Your question is there any key structure?
Well, that's part of the question. Is there any other sort of structure? Other things that you're interested in too. The second part is perhaps you don't see key structure if your bands are very close to the learning surface, but in that case you might still see this intensity jump.
The key structure, I know one case is that I remember one group reporting, I guess it's Rosarno's group reporting some uranium 115 compound showing some high energy kink. The energy scale is large. I don't remember that. But we actually, because the problem is our energy resolution is over 100 electron, so we cannot see any such detailed structure, unfortunately. But if you compare with selenium case and uranium case, they are totally different. I mean, in terms of arguments. For 5F compound, we can clearly see dispersion. But 4F case, most of the case, it's not kind of disclosure, very small disclosure in the vicinity of flame energy, but basically it's not explained by the Translogic regulation. It can be explained by the somehow. But for finite cases, most of the case, Translogic regulation is good study.
With the kink, when you have a kink in dispersion relation, since the intensity is proportional to one with the natural polarization, but if you don't see a kink, you still see a change. So,
I think that's all. Thank you.
Are there any other questions? Let's thank the speaker again.